So this slideshow is the slideshow that is that goes with the book. So like I said, I'll go through some of this, but do you remember how I said that these macromolecules can be very complex? Well, this is one of them. And every one of these little balls in here is an atom. So, you know, of one kind of or another, a carbon or a hydrogen or a nitrogen or a phosphorus. It's all, you know, so you look at this and just see that this is just a crazy structure. And all of these bends are determined by how and where those atoms are bonded to them and what they're bonded to in their next piece in the chain. So when you get into organic chemistry or biochemistry, you get into a lot more of why you get certain structures. Like we never dealt with anything that was quite this chaotic or ridiculous. But I mean, even at the small scale of some of the sugars, you get really kind of like collapsed in on themselves structures, and it changes how they can bind with certain receptors in your body. And from there, what they can and can't do, especially with like the hormones and the steroids and things like that. So, so anyway, here we have a nutritional fact list, and you can see that on here, a lot of what we've talked about here are, you know, we have our fats and we have our carbohydrates and we have our proteins, right? They really don't break it into your nucleic acids because I don't know. I guess people don't like to think about eating DNA of whatever they're eating, but you do. I mean, obviously, anytime you eat anything, you're consuming its DNA. It's part of what's in there. So, so here's your carbohydrates. They have them broken out. Remember, we talked about dietary fiber and how you don't actually get anything from this other than kind of like a cleansing scrub. That's your dietary fiber. It is important to eat. I'm not saying don't eat it. You have your sugars, and in this case, what are we looking at? A box of cereal. So we have sugars, and then we have other carbohydrates. So our other carbohydrates would then be like our wheats and things like that. So they're no longer a dietary fiber. They're going to be starches. So these would be your starches. Here's you just plain old bog standard, you know, glucose, fructose, sucrose, sugars, depending on what's added in there and what your cereal's made out of. And here's your fiber. And you'll see in here that they actually add in a cup of milk as part of your dietary. Because if you were just looking at a box of cereal, obviously, for the most part, you would have, you know, pretty much no fats. Your fat's coming from your milk. So this is what I talked about before. And like I said, so now that we kind of have an idea of these monomers, we can talk a little bit about how they're formed. And you want to pay attention to this. This might show up on your quiz. And how they're combined together, and then also how they're separated apart. And so here's an example. Do you remember when I said you had your zigzaggy line? Well, this zigzaggy line, just remember that every corner here, you have a carbon, right? So if you look at the how this is written out up here for glucose, you have C6H12O6. So that's going to be 1, 2, 3, 4, 5, 6, right? And then you have your 6 oxygens and you have 12 hydrogens. And so with that, you can kind of get an idea of what you might be looking at for structure. But it doesn't tell you anything about whether or not it's a ring structure or if it's a straight structure. So keep that in mind as well too. These two things chemically written out are the same, but structurally are very different. So that's just something to keep in mind. I think just in general, this shouldn't show up either on the test. But so like they're breaking this down here. So you have a hydrate of carbon. So your hydrate's your water and your carbon is so your carbohydrates, right, or carbohydrates. So those are our energies. We talked about that. And then here is some of the process of how these are made. So like I said, you have carbon dioxide in the air, you have water, and you have sunlight as energy through photosynthesis. You make sugars and you make oxygen. So this is what a plant does. Plants also, so this is respiration in humans. Plants also break this sugar back down into energy. So they have a version of the Calvin cycle as well, or the Krebs cycle as well, where they'll take this sugar and they'll break the sugar back down into energy. So they don't just make sugar and store sugar and then never use it. Obviously, they use it to then break it down and turn it into, into their cellular structure and into their cellulose to build their plant. So, but humans use respiration. So this is just the inverse of this. So we get carbon dioxide plus water plus sunlight is equal to a sugar and oxygen. And then humans or other animals, because it's not all about humans, take in the sugar plus breathing in oxygen. We output carbon dioxide and water and energy. So, this is how this process works. So, plants are taking in sunshine, and then we're using that sunshine that they're storing in sugar, and then taking that sunshine and turning it into more cells. So yeah, that's a very, very basic version of this process. And so here's a little bit more of a graphic, but it shows the same thing. So it's the exact same idea, right? So, and we're getting everything stored as a glucose, energy, and it's all circling back around with carbon dioxide being outputted, water being outputted, and and then being the uptake of that back into the trees, and it all circles around. Happy world. All of this cycles around, and none of this chain gets broken. And our version of, like I said, our version of that energy output, and as well as the plant's version of this energy output, is ATP. All right, and then we have our fibers. So you have these soluble fibers. Like I said, it slows down movement of your food. Basically expands in your stomach, makes you feel full, and strips some of the stuff out of your gut as it's going through. And then your non-soluble fibers basically just kind of go through. So, but either way, either soluble fibers or insoluble fibers, we're not digesting those. They just act a little bit different. These are, if you think about like the structure of a plant, so like if, for example, they talk about like apples and things like this, and the inside of an apple, even though there's a ton of sugar in there, obviously there's a lot of sugar in an apple. You taste that. That apple's still made up of cellulose. So, but it's a softer, more pliable cellulose, versus like a celery, which is an insoluble fiber. And like they talk about, this is how laxative works, where basically your body can't really do anything with that, and so it just pushes through your body. So here's we talked about this. So we have our monosaccharides, our disaccharides, and then our polysaccharides. Your oligosaccharides are kind of that in between your disaccharides and your polysaccharides. A lot of times though, a lot of books just go monosaccharides, disaccharides to polysaccharides. But keep in mind that there is this kind of like in-between stage that sometimes gets mentioned. And I don't know if this is in the quiz, but since it's in the slideshow that's related to the book, maybe keep that name in mind. It's part of that group. But if you know these, if you're like, all right, my saccharides are my sugars and my carbohydrates, and you know these three, and then this fourth name is here, you can kind of fit that into where it needs to be, this oligosaccharides. So these readily readily dissolve in water. If you think about it, if you put sucrose into a glass of water, stir it up, so table sugar into water, stir it up, it dissolves, because water's polar. It's a H2O, and these have all these OH groups, and so your likes are going to dissolve your likes. So water's polar, sugar's polar. And you can see here in this diagram, you can see where all the waters are then bonding to all of these OH groups, and essentially they just form around those individual molecules of sugar and suspend them in solution. So they're still there. It doesn't break them down into anything else, at least at this form. You're not breaking anything down, but you have all these hydrogen bonds with the individual water molecules around there. So it gets suspended in that solution. All right, so here's our carbohydrates. Like I said, sometimes you have OH groups off of them. Sometimes you have just hydrogen groups off of them. All of these. So, but what you always have are these carbon chain backbones for them. So, and so basically, depending on how many carbons you have, depending on what's branching off of them, is going to change what they are, how they react to things, and it's also going to change what their name is. And your carbohydrates are going to have this ose ending name to them. So like your glucose, your fructose, some of these that I don't even know, talose. Yeah. But you can, like, once again, do you remember how I said that you can have the same chemical formula? So all of these have the same number of carbons. They all have the same number of hydrogens. They all have the same number of oxygens. But the oxygens are in different places. And you might look at some of these and say, well, they're in the same place, but even flipping them from one side to the other can completely change how they work. So I can't think of it off the top of my head, but there's one of the sugars that was a diet sugar. It might be aspartame. I can't remember off the top of my head. It basically, all it is it looks just like fructose, but the OH is on the other side. And so your body can't use it. So things still taste sweet. It still reacts the same in your mouth, but your body can't then break it down into useful material. So yeah, and all of that, like I said, all of that is just a simple flip of an OH group that's on one side of the structure to the other side of the structure. And something as simple as that can completely change how it can be used in your body. So this is a lipid. So we're going to talk about lipids now. Now that we're through the carbohydrates. Remember how I said it has a polar head, which is hydrophilic, which means it's a water loving, and it has a non-polar tail, which is your hydrophobic, which means it's water fearing, essentially. So we have water loving and water fearing, or water hating. And so most of your lipids are like this. Most of them are going to have a polar head and a non-polar tail, or they're going to have two different regions. And like this says, this is a very simplified look at what this looks like. And this is why your lipids, because they have this hydrophobic area, it's why your oils and your fats and everything will separate from water, don't readily absorb in water, and sit on top of a water structure. So, and so we have just a basic fatty acid. And then you can see, as you start to combine these fatty acids together, you get these triglycerides. So that's 3 fatty acids. You can have a cholesterol, which has got these ring chains to it. Or you can have these phospholipids if you start to add in phosphorus and nitrogen bodies into these. And so, like I said, your cell walls are these phospholipid chains. That's a much better slide of that. And so like I was saying, most of your lipids are polar and nonpolar, and they're insoluble in water. So they don't dissolve in water. And that becomes very important when we start talking about how our cells are made. So your saturated fats are this very straight, no extra linkage in them, bonding. And this is why you get this, they kind of the form of solid. This is the saturateds are single chain, very linear pieces, and it lets them stack together very easily. And by stacking together very easily, then you can get like this really dense fat, if that makes sense, or really dense. So, but your unsaturated fats have got this double bond in that carbon chain there. So it would only have a single hydrogen off. And that double bond kind of gives it a kink in the chain. And because it has a kink in the chain, as you can see in this diagram, they can't sit right next to each other. So that's why they stay liquid. These are your trans fats. They're essentially human made. So they're not a natural, naturally found thing. They work really well for certain things like cooking. And it's why we made them. In some cases, they are also cheaper to make than they are to get the natural thing, which is probably another big reason why we made them. But part of that is we can't metabolize these. So you can have fat in your food that you can't turn into energy. These are just like the sugars that are diet sugars that your body can't use. These trans fats are very similar to. So these are triglycerides. Once again, something that you read about and hear about. Triglycerides are basically it's a glycerol group up here at the top with 3 fatty acid chains coming off of it. So can be represented in any of these manners. So when you hear a triglyceride, that's essentially what this is. And it's something that we make naturally. It's, kind of the fat that we form in our body. And like they say down here, it's, a thermal insulator. It is also long-term metabolic energy storage. So we don't readily store sugar. As you might know, obviously you have sugar moving around in your blood system at any point in time, but that's sugar that you have either taken in or your body has produced back from a fat storage process. So we don't readily absorb or store it as a sugar. We store it as a fat. And you can see here that even though these obviously aren't sugar chains anymore, they're not or carbohydrates, they're still the same building blocks that all of that is made up of. So there's processes in your body that then take these fats and turn them back into sugars, and then those sugars, and through some of that processes you gain ATP even during that process. So basically what a lot of this talks about is how you can have the same number of carbons, and the combination and order and how they're put together really determines how they're used in your body. So these cis isomers and your isomers are all different formings of the same atomic structure. And then here's your cholesterol. Like I said, your cholesterol is a very similar thing, but it does have these benzene rings at the beginning, and then one single 5-carbon ring, and then you have your chain that runs off the end. And so once again, cholesterol it's kind of a big, bulky, rigid fat, as I described down here. And that's part of the reason why cholesterol is considered to be a problem, in that cholesterol, because it's big and bulky like this, has a tendency to clog into places. So like if you have restrictions in arteries and things like that, because it's a bigger molecule and it's suspended in your blood, it will have a tendency to then like catch on, catch up in eddies and form like these pockets of cholesterol. And it's, why people have problems with cholesterol. But cholesterol is, that being said, is still a very important part of, so like, it's why, all cholesterol is not bad. And even some of the bad cholesterol is not all bad. You need cholesterol in your body. It's a building block and a functional part of your body. And it's your precursor to your steroid. All right. And then finally, we'll talk about this, and then I'll go back and I'll talk about those two different types of bonding, and then I think we'll call it good for the night. But this is our waxes and soaps. And this is why waxes and soaps do what waxes and soaps do. All right. So you get these big, giant chains, right? With this little head up here. And this top part of this is hydrophobic or hydrophilic, and these chains are hydrophilic, right? And so if you drip wax onto water, it floats on the surface. It doesn't combine any, even hot wax, and you stir it up into hot water, it's still going to like be in its own little like pocket. Same thing with your soaps, though it's not as obvious. And so what soap does, and this is just a really good drawing of it, is you've got this soluble water end, right? And you got this big, long, non-polar chain or tail on there. And so you wash with soap, and you get all of these soap molecules in the water, and the little tails will go, and they'll go to the pieces of dirt, and they stick to the pieces of dirt, and the little head, and to get away from the water, and the little heads all go out and stick to the water. So then those little, basically you get these balls of soap that are around your pieces of dirt, and they detach them from your skin, and they make that dirt then float in the water, because a lot of your dirts might be insoluble in water as well. So like, say you have oil on your hands, obviously oil is an insoluble hydrophobic material. It's a fat. Motor oil is as well. It's a hydrocarbon, but it's still essentially this. And so the soap will form around those hydrophobic pieces, make them soluble in water, because the soap is now surrounding it with these hydrophilic heads. And then it allows you to wash that hydrophobic piece of grime or grit or dirt or, bacteria or whatever off of your body. So soaps, that's how they work. All right. So I want to show you guys really quick, because I do know that this is in the quiz. This is your dehydration synthesis. Basically what this is showing is you have these two monomers with OH groups on them. And when you take two of your monomers and combine them together, you get a water out, which is why it's called dehydration synthesis. So basically you're taking a water away from these two, dehydrating them, and combining them together to get a polymer and a water. Okay. And so this drawing's maybe a tiny bit confusing. That's an arrow. That is not a bond. Okay. So this water is not connected to this polymer. This water is completely separate. So that's how dehydration synthesis works. Here's some other other drawings of it where you have these two glucose, you have dehydration synthesis, and you end up with maltose and a water. Okay. Same thing to make sucrose. If glucose and fructose go together, you get a water out of this OH and this H, and then you get sucrose together. And then this is what's called hydrolysis. So hydrolysis is the reverse of that. So you have a polymer, you add water to that polymer, and it breaks this bond here, creates an OH group on this one and an OH group on this one. Does that make sense?